So let's go over some examples, and we'll kind of look to some examples to kind of guide us along. So for the polynomial example that I talked about before, I'm going to be use this notation right here to show that these vectors or functions in the vector space are orthogonal to one another. So we'll just do the first couple. We'll get the dot or inner product between 1 and x squared. And here we'll just use a simple weighting function, and we'll use the weight function 1. This is the integral from a to b of the weight function, which is 1, times the function 1 times x squared dx, which is the integral from a to b of x squared dx, which is going to be x cubed over 3 from b to a, which is b cubed minus a cubed over 3. And this is non-zero, for positive or even negative values of a and b. So 1 and x squared are not orthogonal with the chosen weight function. If you instead look at the inner product, say, of 1 with x, you obtain the integral from a to b of the weight function times the function 1 times the function x, which is the integral from a to b of x, which is b squared minus a squared over 2, which is again non-zero, unless a is equal to negative b. In which case you would have that this is equal to 0. So these are not orthogonal unless the interval I is a symmetric interval surrounding 0 of the form negative b comma b. And there are whole classes of polynomials and weight functions that are very, very useful in applied mathematics. I'll list the first few, what are called Legendre polynomials. This is after the Adrienne Marie Legendre, who discovered them in 1782. This is a system of complete and orthogonal polynomials with a vast number of applications. These are typically taken with the weight function as 1, and the interval I is the interval from -1 to 1. But the Legendre polynomials can be defined in a number of different ways. They can be defined recursively. They can also be defined in terms of a nice formula. Fn of x is equal to 1 over 2 to the n times n factorial times the nth derivative of x squared minus 1 to the n. And the first couple of these I'll list as follows. For n equals 0, the first polynomial is 1. For n equals 1, x is a member of this Legendre polynomials, and if you go through and either recursively or directly apply this formula, and for n equals 2, you get the polynomial 1/2 3x squared minus 1. For n equals 3, you get the polynomial 1/2 5x cubed minus 3x, and so on and so forth. You can go down and define infinitely many Legendre polynomials, and these all will be orthogonal to one another if you go through and use the inner product with a weight function 1 on the interval from -1 to 1. Other classes of very important polynomials include Jacobi polynomials, they're called the Hermite polynomials, Laguerre polynomials, and the list goes on and on. All of these have very important applications in modern applied mathematics, in physics, as well as in engineering mathematics. So the next example is going to be really important in terms of where we're going. Let's consider the following functions. Let's consider the functions Sn of x, which is just the sine function of n times x. And we'll consider the function Cm of x, which is the cosine function of m times x. We'll also set the weighting function to be equal to 1. So the inner product of Sn with CM. And we'll also choose our interval I as well. Here's the interval I to be from 0 to 2 pi. Actually, let's choose it to be from negative pi to pi. This is the integral from negative pi to pi of 1 times sine of nx times cosine of mx dx and this is an integral that we can do very succinctly using what's called tabular integration, which is two separate integration by parts in a cyclic integration. So tabular integration is more general. We can do integration by parts any number of times that we want, but you'll recall that we know that if we do integration by parts on this two separate times, we'll end up getting back to the original functions that we started with, modified by a multiplication factor. So for tabular integration by parts, you have a column for the nth derivative of u, and a column for the nth antiderivative of the v that you choose in your integration by parts. And this is really the easiest way of going through and doing integration by parts if you know that you're going to have to be doing multiple steps of an integration by parts. So for n equals 0, we'll choose sine of nx. And cosine of mx. And then for n equals 1, the derivative of sine of nx is going to be n times cosine of nx. And the antiderivative of cosine of mx is going to be 1 over m times sine of mx. And when we do the next integration by parts, we'll have the derivative of cosine of nx, or n times cosine of nx, which is negative n squared sine of nx. And the antiderivative of sine of mx is going to be negative 1 over m squared cosine of mx. So this is called tabular integration by parts. And whenever you have to do multiple integration by parts, it's really the most efficient way of going through and getting all of the terms in the resulting integration by parts. So when you do your first integration by parts, you're going to end up getting u times v. Remember, the integration by parts formula is the integral of u dv is equal to uv minus the integral of v du. And this is what's called a cyclic integration by parts problem, where you're going to have to do two integration by parts, and we'll end up getting back to the original combination of functions that we started with. So we'll call this value that we're looking to find the value I. And maybe not I, because we're already using I right here. So we'll call this value L. So when we do the first integration by parts, we have that L is equal to, then it'll be positive the integral of positive this times this so sine of nx times 1 over m cosine of mx, sine of mx, evaluated from pi to negative pi, and this will be minus the integral from negative pi to pi of n cosine of nx times 1 over m sine of mx dx. And this is just kind of illustrating why one integration by parts isn't very helpful here. But we'll see then when we do, if we do two integration by parts. So we do an integration by parts on this expression right here. Your u is going to be this, and your dv is going to be this term right here, which is going to give you something that we can work with. And what's nice about the tabular method of integration is you don't even have to go through this step initially. And so if we forget about just this first integration by parts step, we just apply the integration by parts knowing that we're going to do it 2 times in this table. We have a very speedy method, or much better quick method for going through and doing this. So we'll delete this right here. And then we know that our integral L is going to be positive this times this, which is 1 over m times sine of nx cosine of, or sine of mx and then when you do the integration by parts again on this, you're going to get another term which is positive or negative this times this right here. So it'll be minus n times cosine of nx times negative 1 over m squared cosine of mx and then because we're terminating the integration by parts, this is from negative pi to pi. We have one final term, which is an integral term. It's the integral of this times this positive. So plus the integral from negative pi to pi of negative n squared sine of nx times negative 1 over m squared cosine of nx dx. And so L is going to be equal to sine of nx sine of mx over m plus n cosine of nx cosine of mx over m squared from pi to negative pi plus n squared over m squared integral from negative pi to pi of sine of nx cosine of mx dx. Which in fact is the exact same thing that we started with. We're looking for the integral of sine of nx times cosine of mx. So this reduces to the equation where this entire thing is equal to L, which is what we're looking for. And so if I subtract this term from both sides, I'm left with L times 1 minus n squared over m squared is equal to this. Or if n is not equal to m, so this is not 0, and L is equal to this expression divided by one minus n squared over m squared. And it looks rather long, but I assure you that it's not. If you go through and plug in, we're left here with that L is going to be equal to sine of n pi sine of m pi plus n cosine of n pi cosine of m pi all divided by 1 minus n squared over m squared and this entire thing minus sine of negative n pi sine of negative m pi plus n times cosine of negative n pi cosine of negative m pi. all divided by 1 minus n squared over m squared. And this is 0. This is 0. If you remember what the sine function is, that the value any integer times pi. And this value right here cancels with this value right here. So we've directly shown that L, or the integral of sine of nx times cosine of mx dx from negative pi to pi is equal to 0. So these two functions are orthogonal on this interval. And as it turns out, this idea is going to be for us the basis of Fourier series. The orthogonality of trigonometric functions, and using this to our advantage to go through and actually come up with some very clever representations for continuous functions. Now, I've shown the long way of going through and exactly showing this relationship, so we'll call this method 1 here, of finding L. But a much easier way of going through and doing this is using the fact that sine of nx is an odd function, and cosine of nx is an even function. So sine of nx multiplied by cosine of mx is an odd function, and so the integral from negative pi to pi is an integral over a symmetric interval, and whenever you're integrating an odd function, over a symmetric integral, that integral has to be equal to 0. Remember that if f is an odd function, then f odd of negative x will be equal to negative f of x. And if f is an even function, f of negative x will be equal to just f even of x itself. In terms of graphs of the function, if an odd function, say, looks like this to the right of the x-axis, the right of x equals 0, so the right of the y-axis, to the left of the y-axis, it's going to be flipped across both the x and y planes. Whereas for an even function, if f is an even function, if f looks like this, I'll make it look a little bit different. This maybe for positive values of x, and for negative values of x, it's going to be flipped and look like this. But it still has the exact same shape as the original function itself, just flipped. So for any odd function, the integral of the odd function over a symmetric interval is going to be 0, and for any even function, we can go through and prove that. So we're going from negative a to a for an odd function. The integral from negative a to a of this odd function will be 0, whereas for an even function, the integral from negative a to a of f of x dx will always be 2 times the integral from 0 to a of f even of x. This is a much faster way of going through and getting the result that we just proved. But I think it's useful to see both ways because it really shows that for a lot of these functions that we'll see, we need to be able to go through and both sometimes use mathematical simplifications as well as be able to go through and brute force do the actual integrals using integration techniques from Calculus 2. So the last example that I want to consider is really an incredible example, which is going to kick off our study of Fourier series. And the idea here is the following. So suppose we wish to approximate the function f of x, where f of x is the function x times pi minus x on the interval from 0 to pi with a function of the form g of x is equal to c1 sine of x plus c2 sine of 2x plus c3 sine of 3x, and then we'll add a fourth term as well, plus c4 sine of 4x. And just for simplicity, I'm going to call this function sine of x g1 of x. I'll call this function g2 of x. This function g3 of x. This function g4 of x. And we want to note that approximate here, I say approximate, the term approximate only has meaning in terms of a distance measurement. Specifically, what we're going to do is we're going to use the idea developed before, and we're going to use the inner product and norm that we introduced before for function spaces on the function space of continuous functions from 0 to pi. And there's two things that you want to see here. The first is that the inner product of gn of x with gm of x so any of these two functions, any combination of these two functions, is going to be one of two values. If n is not equal to m, it'll be the integral from 0 to pi of sine of nx times sine of mx dx. And if n is equal to m, this will be the integral from 0 to pi of sine squared of nx. Because this is just the inner product of these two sine functions. And then with n equals m, then this will just be the inner product of sine of nx with sine of nx, which is just, this is the same thing as the norm of sine of nx squared. So it'd be good practice for you to go through and get these values, both of these integrals. But these functions, this integral will always be 0 when n is not equal to m. And this integral, when the inner product of gn and gm, and we don't really actually want to include n and x here, so we can simplify our notation, kind of shorten our notation a little bit. But it's relatively easy to go through like I did before and show that this integral will always be 0, and this integral right here is always going to be for any value of n in m when n equals m, so for any value of n, this integral will always be pi over 2. So each one of these functions, g1, g2, g3, g4, are orthogonal to one another in the function space C from 0 to pi. And what's a very, very, very powerful idea here is to think of what a projection looks like. So to find our approximation of f with this function g of x, we're going to be using the idea of projection from finite dimensional vector spaces that we had from before. So recall that if a and b are two vectors, this is in a finite dimensional vector space, the projection, which is a vector, the projection vector of A in the direction of B is defined as the magnitude of A cosine of the angle theta times the unit vector in the B direction, which is the same thing as the dot product of A with B divided by the magnitude of B times B hat, which is the vector B over the magnitude of B. So this is A dot B over the length of B squared times the vector B. This is in projection in Rn, n-dimensional space. So an n-dimensional Euclidean space. And using this idea, and the fact that Gn and Gm are orthogonal to one another, we can develop a direct analog of projection. Say that the projection of the function f in the direction of the function, the direction, with quotations there, because in infinite dimensional vector space we don't really have a concept of direction. So the projection of the function f onto gi is going to be equal to the inner product of f with gi divided by the size or magnitude of gi times gi itself, in direct analog to this formula right here, our projection formula from or finite dimensional vector space. But this is now an infinite dimensional projection, using the inner product for functions and the norm for functions. And what's incredible here is we define our approximation function, fa, and define this approximation function as the sum of the projection in each one of these, along each one of these functions, gi. So the first projection is f1 comma, or f comma g1, over the norm of G1 times G1 plus F comma G2 over the norm of G2 times G2 plus F comma G3 over the norm of G3 times G3 plus F comma G4 over the norm of G4 times G4. And for each one of these norms, we know what it's going to be. We already, when you go through and calculate this value right here, you have the norm G4. Oh, and these should all be squared as well. So for instance, for each one of these, the norm of Gi squared, or Gp squared, we'll say, is just the integral of sine of px dx squared 0 to pi, which is relatively easy to show as pi over 2. And furthermore, when you go through and calculate, let me make some space here so you have a little bit more room on this page. For each one of these integrals, you have to go through and calculate. For f, the inner product of f and gp, this is going to be the integral from 0 to pi of f of x, which is x times pi minus x times sine of px dx, which ends up being, when you go through and if you do integration by parts here to get this integral, this ends up simplifying to pi times p times sine of p pi plus 2 minus 2 cosine of p times pi over p cubed. And sine of p pi is always 0 for any value of p. And furthermore, cosine of p pi is negative 1 to the p. So this inner product is always going to be 2 times 1 minus negative 1 to the p over p cubed. And this would be a good integral to practice, going through and practicing your integration by parts from Calculus 2. But this is giving us that our approximation function, and actually our best approximation function here, is expressed in terms of a projection of our normal function f, or the function that we're approximating, onto each one of these orthogonal unit vectors, and it's actually onto a 4-dimensional subspace of this infinite dimensional vector space of continuous functions, where each one of these values, this is C1, this is C2, this value right here is C3, and this coefficient right here is C4. So if we go through and calculate these coefficients, well, we've already calculated all the integrals, so using this to calculate the coefficients isn't too bad. C1, really we have for any CP, this is the inner product of F with GP divided by the norm of GP. So C1, we plug into it, is going to be 2 times 1 minus negative 1 over 1 divided by pi over 2, which is 8 over pi. C2 is going to be equal to, when you plug in p equals 2 here, this is 0, because you get 1 minus negative 1 squared is 1 minus 1, or 0. C3 is equal to 2 times 1 minus negative 1 cubed over 3 cubed, which is 27, over pi over 2. And this simplifies to 8 over 27 times pi. And then similarly, for the same reason as C2, C4 is also 0, because 1 minus negative 1 to the 4th is 0. So then our approximation function, FA, becomes 8 over pi times sine of x plus 1 over 27 times sine of 3x. And this is really amazing, because this gives us a direct method, right, of taking sums of trigonometric functions and using them to approximate continuous functions on given intervals. Now, this is essentially the topic of Fourier series, and this has very, very wide consequences and applications in engineering and mathematics. But the idea is that we want to kind of figure out how good this approximation is, and one way of doing that is with the norm. So we call the L2 error is the norm, going to be the norm of f minus fa. This is the function norm that we introduced before, which is just the square root of the inner product of the function f minus fa with itself, which is a rather long thing to compute, but it's not too bad, and I definitely recommend going through and using this as practice, to go through and practice your integration techniques. This is the square root of the integral of 8 over pi times sine of x plus 1 over 27 times sine of 3x minus f of x, which is x times pi minus x. This has to be squared, and we have to get the square root of this. Because we're taking the norm. So in order to evaluate this integral, I would expand this. So I expand this square right here, and it is rather long when you go through and do the integral. You have to break it into a number of different pieces, but when all is said and done, you get the exact value, pi to the 5th over 30 minus 23,360 over 729 times pi, and it's the square root of this. So the integral ends up being the value under the square root, and you have to take the square root of this to get the value of this norm. But if you evaluate this norm, you get that it's approximately equal to 0.0277 0.110. So this approximation is, or the L2 error of this approximation is not too bad. It's relatively small. And if you include more terms in this sum, in our approximation sum, so C5, C6, C7, it will only get better and better and better. And you can directly visualize this. Right? Let's say we want to open up and get a picture of how good this approximation is. It's directly possible to do this. So let's open up window capture of, this is our function right here, and I'll change it to the black. So we see our function right here, and color the approximation in red. So this is our function, this is the resulting approximation, and if we turn on a plot of the approximation function, and we only really want to go from 0 to pi here, we're seeing that we have a very good agreement between the function f and the approximation function of sines. And the total L2 error of this approximation we calculated before, it's 0.02, around 0.02. So Fourier series will be essentially taking this idea and going very, very far with it, and exploring many of the different applications this has in engineering. But I hope this is a good introduction to some of the mathematics that we'll be using in the next couple lectures, and I hope you learned something today. But this will end today's lecture, so thank you very much for tuning in, and I hope you had a great day.